In this video, we are discussing about the evaluation of special type of integrals using residue theorem. Type 2, that is integral of the form integral minus infinity to infinity f of x divided by g of x dx. For that, to get the variation of x from minus infinity to infinity, we take the real axis from minus r to r and the semicircle connecting minus r to r as r tends to infinity, which means here the integral is of the form integral minus infinity to infinity f of x by g of x dx. Here the function and integration is with respect to x. First of all, we want to convert this integral in terms of z, that is replacing x by z. Then we want to give the limits of integration with respect to z. For that, we are considering the region minus r to r and a semicircle connecting minus r to r. That is, first of all, in minus infinity to infinity f of x by g of x dx is equal to integral over c f of z by g of z dz, and this region is taken as the entire upper half plane including the real axis, which means a semicircle connecting minus r to r as r tends to infinity means the entire upper half plane including the real axis. Okay, so this is the type 2 integral. Moving to problems, evaluate integral minus infinity to infinity 1 divided by x square plus 1 dx. Here the function and integration is with respect to x. First of all, we want to convert it in terms of z. So integral over c 1 divided by z square plus 1 dz. Next step is finding the poles. Here the poles are given by z square plus 1 equal to 0, that is z equal to plus or minus I. Next, which point lies in the upper half plane including the real axis? Here z equal to I lies on the upper half plane. So we want to find the residue at z equal to I. So residue at z equal to I. This is a simple pole. So limit z tending to I, z minus I into f of z, that is 1 divided by z minus I into z plus I. Common terms is cancelled. Then answer is 1 by 2i. Therefore, integral minus infinity to infinity 1 divided by x square plus 1 dx is equal to, by Cauchy's residue theorem, it is 2 pi I into sum of residues, that is 2 pi I into 1 by 2i, that is equal to pi, which is the answer. Second problem, evaluate integral 0 to infinity x square divided by x square plus 4 the whole square dx. Here the function and integration is with respect to x, but here the limit is from 0 to infinity. Our type 2 is integral minus infinity to infinity. So we want to rewrite this integral with the limit of integration as minus infinity to infinity. For that, we have a result. If the function is an even function, then integral minus a to a f of x dx is written as 2 times integral 0 to a f of x dx. So integral 0 to a f of x dx will be 1 by 2 into integral minus a to a f of x dx. Here the function is x square divided by x square plus 4 the whole square. Here it is an even function, so we can rewrite this integral as 1 by 2 into integral minus infinity to infinity x square divided by z square plus 4 the whole square dx. Then in terms of z, this is equal to 1 by 2 integral minus infinity to infinity is replaced by c, and z square divided by z square plus 4 the whole square dz, which is equation number 1. Then the poles are given by z square plus 4 equal to 0, that is z equal to plus or minus 2i. This is a pole of order 2. Okay, here z equal to 2i lies in the upper half plane. So residue at z equal to 2i is equal to, it is a pole of order 2. Therefore 1 by 2 minus 1 factorial into limit z tending to 2i d by dz of z minus 2i the whole square into function, that is 1 by 2 into z square divided by z minus 2i the whole square into z plus 2i the whole square, that is equal to 1 by 2 into limit z tending to 2i d by dz of z square divided by z plus 2i the whole square, that is u by v method or quotient rule. And finding the derivative and put z equal to 2i, we can answer as minus I by 16 as the residue. Therefore, equation 1 will be integral 0 to infinity x square divided by x square plus 4 the whole square dx is equal to 1 by 2 into integral minus infinity to infinity, that is integral over c z square divided by z square plus 4 whole square dz as 2 pi I into sum of residues, that is 2 pi I into minus I by 16. So the answer is pi by 8. This is the method to evaluate this type of integral using residue theorem.